Dr. P. Nagraj. He is currently working as Assistant Professor in the Department of Chemistry, Anna University, Chennai. Earlier, he worked as a scientist in charge at Spices Board of India for 5 years in research and development and also in quality control laboratory. He has finished his PhD in organic chemistry at IIT Delhi. He has also done his MSc Chemical Science at Pondicherry Central University. He has published 6 papers in international journal and also participated several international events in India and abroad. He has attended several conferences and delivered lecture as keynote speaker and also undergone 12 training programs. His area of research interests are isolation, synthesis of natural products and evaluation of their biological activities, carbohydrate-based natural product synthesis, enzyme catalyst organic synthesis, green chemistry, medicinal aspects of spices and spice products.
Welcome to UGC lecture series in Polymer Science. Today we are going to discuss biopolymers, especially polylactic acid and polycaprolactam, and applications, synthesis, uses, all these things we are going to study today classes. Today content is what is polylactic acids and the history of polylactic acids, uses and applications of polylactic acids, and how synthesis of polylactic acids, and again another part is what is the polyamides, synthesis and its uses of polyamides, and questions. Waste, the waste can be differentiated like this in the flowchart diagram, where the paper based waste, it is a major huge amount which is 36%, followed by others. The least one is other waste like 3%, wood 6 and glass 6, rubber, leather, textiles are 7%, metals 8%, and plastics 11%, and food scraps 11, followed by yard trimmings 12. So, majority of waste belongs to paper related to waste. The breakdown of waste which is getting biodegradable depend upon the time, especially you can go for cotton and rags which is takes 1 to 5 months, and in case of polylactic acid composted 45 to 60 days, whereas in case of paper 2 to 5 months, and orange peels 6 months, cigarette butts 1 to 12 years, and plastic coated paper milk cottons 5 years, and plastic bags 10 to 20 years, leather shoes 25 to 40 years, nylon fabric 30 to 40 years, tin cans 50 to 100 years, aluminum cans 80 to 100 years, and plastic 6-pack holder rings 450 years, and glass bottles 1,000,000 years, plastic bottles forever. So, this is what the table which shows that the biodegradable, which is especially plastic bottles and glass bottles, which is several years, whereas in case of cotton, which is again biopolymer which is made up of cellulose, which is 1 to 5 months, followed by polylactic acid which is almost 60 days or less than 2 months, which is getting biodegradable. This is the beauty of polylactic acids, which gets biodegraded within 45 days to 60 days. And the scope of this lecture is plant build in Midwest, 2 key assumptions: built next to corn milling facility, dextrose productions can be increased with increased demand of polylactic acids, total capacity of 500 million pounds per year. Cargill and Dow Chemicals co-venture resulted in a 300 million pound polymer plant, which is second plant in planning. So, history of polylactic acid in 1932, Crothers DuPont company created polylactic acid. 1954, again DuPont patented Crothers process, and extremely high cost of production. 1997, Cargill Dow Polymers LLC forms. In 2001, 300 million pounds produced at the Blair, Nebraska plant. This is the plant where the polylactic acid which is produced in the large quantity in the place of Nebraska. Properties of polylactic acids: polylactic acid which is insoluble in water, moisture and grease resistant, biodegradable and compostable, clarity and glassiness similar to its other plastic competitors, requires 20 to 50% less fossil fuels to produce than regular plastics, comparable physical properties to polyethylene terephthalate PET. So, this is the property, especially physical and chemical properties of polylactic acids. So, based on that, which is available biopolymers which can be easily biodegradable. That is the beauty, whatever plastic material which if we are making it biodegradable, that is eco friendly plastics or polymer which is encouraged to produce and use nowadays. So, uses: single use items such as plates, utensils, cups and film wrap, plastic bottling and fast food companies, paper coatings, clothing fibers, compost bags, biomedical field. So, these are all the applications of polylactic acids which is used in all the field, especially wherever which is used which is easily biodegradable, which we have seen in the previous slides, which is degrade 45 to 60 days. That is the beauty of this polylactic acids. Current market price: plastics in 2000 150 million tons, in case of 2010 expected to reach 258 million tons. Whereas, in case of biodegradable plastics 1997 20 million pounds, in case of 2004 expected to capture 20% of the market for plastics. Current selling prices for polylactic acid is 1.5 and in current selling price of PET is 0.06. So, polylactic acid slightly higher rate, whereas which is a biodegradable nature, if we are producing low cost, that will be more ideal for application point of view. The chemistry of fermentation step. So, bacteria breaks down one molecule of dextrose to form 2 molecules of lactic acid. This is the dextrose, the sugar molecules bacteria decomposes to convert to 2 molecules of lactic acids. So, the lactic acids which is carbon CH3 which is attached to CHOH, that carbon attached to COOH, where carboxylic acid and hydroxy group which is present in the adjacent carbon, that is lactic acids. The chemistry of lactide formation, again 2 molecules of lactic acid which is combined together to form lactide. 2 molecules of lactic acid combined to form 1 molecule of lactide. Elimination of water molecule. If you remove water molecule from 2 monomer of these, and you will get a lactide which is a adduct. So, this lactide, the lactide polymerizes through ring opening polymerization to a molecular weight of approximately 30,000. So, this is the lactide which is undergo ring opening polymerization, means this is the ring which undergo opening to produce this unit, lactide unit as the monomer, and which is extended to get a polymer. The monomer unit is lactide. The polymer is polylactic acid. Polylactic acid belongs to the family of aliphatic polyester and it is considered biodegradable and combustible. That is, ability of degrading a material under the action of microorganism in a humid environment to produce biomass and carbon dioxide. So, this is what biodegradable means, the compound which should get degraded or chemically changed to other compound in presence of microorganism, and that is what happening in case of polylactic acid, which is a natural polymer which is gets converted to other material in presence of microorganism, that is called biodegradable. And PLA is the thermoplastic, that means if you are heating it will get melt, or if you are cooling it will get hard. PLA is a thermoplastic, high strength, high modulus polymer which can be made from annually renewable resources to yield articles for use in either industrial packaging field or biocompatible or bioabsorbable medical device market. So, these are all the applications where polylactic acid which is used in the industry level. So, polylactide, lactic acid, L-lactic acid and D-lactic acid depend. This is a stereochemistry, which is L means the hydroxy group which is present in the molecule which is left side the structure, whereas in case of the hydroxy group which is in the right side, that will produce D-lactic acid. Based on the hydroxy group purely lactic acid, D-lactic acid means the hydroxy group which should present on the right side, whereas L-lactic acid the hydroxy group which present on the left side. So, which produce a lactide. So, lactide also have a stereoisomer where L-lactide, again this is L-lactide, the another one is a D-lactide, and this is a meso compound where D and L both are present as a mixture. All the three commonly known as cyclic dimers. So, glycolide, this is simple structure of glycolide where the carbon which is have attachment either methyl group or hydrogen, then that is lactide. So, this is another pictorial representation where lactic acid, this is the lactic acid CH3, CHOH and OH, COOH. So, lactic acid which will produce low molecular weight pre-polymer, molecular weight 2000 to 10,000, this is a lactide, and this is small unit or small polymer chain which is azeotropic dehydration, condensation, removal of water will produce high molecular weight pre-polymer more than 1 lakh molecular weight, and a chain coupling agent, if you add both two chains will combine together will give a big or longer chain, whereas in case of lactide here another possibility is there, lactic acid which will give low molecular weight pre-polymer, the molecular weight 1000 to 5000 which is shown here, which will undergo lactonization will give a lactide. This lactide can undergo ring opening polymerization will give high molecular weight pre-polymer, molecular weight greater than 1 lakh. So, this is the scheme which tells that the lactic acids either three way which undergo either in the way it will produce low molecular weight, and you can do the chain coupling agent, you can make high molecular weight polymer, or this lactic acid will produce low molecular weight polymer which will undergo formation of lactide. The lactide further undergo ring opening polymerization will produce high molecular weight polymer, the molecular weight greater than 1 lakh. So, polylactide again, if you take the lactide which is shown here, you use a catalyst, what will happen? The ring will get opened to produce a polylactic acid. So, again polylactic acid CH3 CHCOO which is the monomer unit present here. The dehydration of removal of water molecule from the polylactic acid will produce polylactide. The polylactide will undergo ring opening polymerization will produce polylactic acid. Ring opening lactide polymerizations, there are so many ways here shown here, cationic polymerization and anionic polymerization. In case of cationic polymerization, protic acids HBr, HCl, trifluic acids etc. can be used. In case of Lewis acid, zinc chloride, aluminum trichloride etc. can be used. In case of alkylating or acylating agents like a triethyl oxytetraborane, these kind of compounds can be used as a alkylating or acylating agent in case of cationic polymerization. In case of anionic polymerization, proceeds by nucleophilic reactions of the anion with the carbonyl and the subsequent acyl oxygen cleavage. This produces an alkoxide N group which continues propagate. So, this is simply the lactide can undergo polymerization either in case of cationic polymerization or anionic polymerization. Cationic polymerization can induce either by using some cationic catalyst like which can be protic acids HBr, HCl, whatever acid can produce proton H plus. This kind of acids known as protic acids. Protic acids can start or initiate the polymerization which is undergo cationic polymerization. Other class of catalyst are Lewis acids which is electron deficient nature, that also can give the cationic polymerization, and another class of polymerization which is anionic, that means O minus or the negative charge which can attack the lactide which will undergo polymerization to produce polylactic acid. The next one is coordination or insertion polymerization, use less reactive metal carboxylate oxides and alkoxides. Polymerization by tin, zinc, aluminum and other heavy metal catalyst with tin 2 and zinc yielding the purest polymers. So, this is a third class of polymerization. Number 1 is cationic, number 2 anionic, third one is coordination polymerization. That means coordination means it should have some central metal ion to coordinate, then followed by ring opening you will get a polymer. Especially central metal ion here, tin, zinc, aluminum and other heavy metals used as a catalyst. Here shown diagram which deals with anionic polymerizations, where the lactide, this is the structure of lactide, the anion will be either O or minus, the metal will be the counter ion M plus. So, this alkoxy metal ion, the metal will be linked with alkoxide ion, which will undergo attack the carbonyl group. I will show here. This alkoxide ion will directly attack the carbonyl group of the oxygen. What will happen? It will attack this bond, then the bond will get opened, then it will come back here. This ether link will get cleave. So, O minus will produce. This is what shown here, ROO and CH3O. Then the other molecule will link the other structure, will produce like this. The O minus will be exist and the counter ion M plus, which will be stabilize the negative charge. This is the simplest way of explain how the anion to attack the lactide to produce a anionic polymer. This is the again coordination and insertion of polymerization. The lactide here, 2 carbonyl carbon which is present here, the metal ion especially tin which is coordination with the carbonyl oxygen and which will undergo initiation of the product, or on the other hand what will happen after the coordination polymerization, the lactide which is linked to the central metal ion can give the initial product, and that will give this kind of ring opening, the OR, CO, CH3O, CO, OH, the acid will produce, thus will give undergo removal of water to produce a lactide, that if you keep on add molecule with the central metal ion to produce a polylactic acid as a polymer. So, polylactic acid is a biodegradable polymer wafer, roughly the size of biodegradable polymer wafers can be implanted in specific places in the brain after cancer surgery to deliver cancer killing drugs at the controlled rate. Photocourtesy of Gulford Pharmaceuticals. That means, if you are somebody doing the treatment of cancer, there if you want to give the drug to deliver to the particular in the cancer affected place. So, this is act as a drug delivery medium, it will undergo in the body and it will take the drugs and it will release wherever it is required in the body. So, which is I already mentioned, which is a biodegradable nature, which will degrade as early as possible. So, act as a drug carrier or taking to drug to the target oriented drug release. This is the flow chart diagram which is shown here. Industrial scale to produce this polylactic acid, especially if you take dextrose, ammonia, water, this much quantity, which will undergo fermentation to give in presence of ammonium lactate, it will give esterification, or you can on the other hand you can take butanol, it will give both two will give esterification, will give butyl lactate, then which will undergo distillation to produce ammonia gas will evolve, butyl lactate which undergo hydrolysis, either it can give butanol sulfuric acid, and the lactic acid which undergo to produce lactide formation, then lactide which undergo polymerization to produce polylactic acid plus water. This is how the flow chart which tells that the starting material which can be converted to undergo fermentation, which will produce esterification followed by distillation and hydrolysis and lactide formation and followed by polymerization will produce a polylactic acid. So, key design assumptions: industrial scale equipment behave similarly to laboratory testing equipment. The equipment from differing experiment is compatible. So, industrial scale if you want to make, depend upon the quantity you want to produce, such a method or flow chart you can make, accordingly you can prepare the polylactic acids. So, for fermentation there are two stage membrane cell recycle bioreactor with ammonia resistant strain of Lactobacillus rhamnosus. High productivity, more feasible for scale up. Electrokinetic bioreactor relieves product inhibitions, alleviates need for additional pH control in chemical. So, this is inside fermentation. Another one is deals with the neutralization of the lactide formations. Calcium carbonate, sodium hydroxide, which is act as a neutralizing agent. Also ammonia, easy to recycle, no salt formations, does not damage in the cells. Electrodialysis does not introduce additional chemical or separations. So, this is the beauty if you are adding calcium carbonate or sodium hydroxide as a neutralization agent. So, polymerization catalyst, tin octanate, catalyst used by Cargill Dow and less expensive, harmful to humans and the environment. So, wherever you are going for tin which is a carcinogenic in nature. So, if you are using large quantity of tin which will produce cancer in our human health. So, which is danger to use, and also zinc beta diaminate complex catalyst. Alternatively, in order to avoid this kind of harmful tin, people use the zinc beta diaminate complex catalyst, gives 94% conversion in 30 minutes, immobilized in a packed bed. So, the conversion rate also very high in case of using zinc beta diaminate, whereas using zinc octanate which is harmful to human as well as in the environment. In case of safety point of view, which is flammable in nature, corrosive and explosion hazards, careful chemical storage placements, a strict personal protective equipment policies, implementation of process control, execution of extensive safety procedures. So, these are all the safety measures if we are going to do in the large scale, especially industrial scale to produce polylactic acid. So, these are all the safety measures you have to follow it. And in case of environmental concern, produces N-butanol waste stream which needs to be treated, whatever the side product which is N-butanol which is going to be, you have to treat it and you can reuse it. Further research is necessary to avoid this kind of wastage. All process solvents and catalyst requires secondary containment and careful monitoring. So, another class of biopolymer is polycaprolactam. What is a caprolactam? Which is a cyclic amides. This is shown here. This is amide, especially this NHCO bond which is called amide. That means the carboxylic acid which is having CO and amino group which is having NH2, both do combinedly to form a amide, if it is cyclic in nature, which is called cyclic amides. This is what here the N may varies accordingly. If it is N is 2 beta propiolactam, the N is 3 gamma butyrolactam, if N is 4 delta valorolactam, if N is 5 caprolactams. So, which is caprolactam as a cyclic amides, which is one of the monomer which can undergo ring opening polymerization to produce a polymer. The N vary accordingly depend upon the number of unit which is attached or which is going to give a polymer. So, this is shown here. If it is N is 5 which is caprolactam, we are going to study the caprolactam in details. Why caprolactam is important one? Here this is phenol. Phenol undergo hydrogenation to produce cyclohexanol. The cyclohexanol which is undergo oxidation to produce cyclohexanone. So, phenol undergo hydrogenation will produce cyclohexanol. Further, which undergo oxidation, you can use any oxidizing agent which is a secondary hydroxy group which you can undergo oxidation to produce a ketone. Again this ketone which is followed by react with hydroxylamine in presence of hydroxylamine to produce N-hydroxy keto derivatives which is called oxime. This oxime which is a compound in presence of sulfuric acid, acid medium, what will happen? Protonation occurs in the hydroxy group to produce better leaving group water molecule, and due to the ring expansion this bond gets break and which will attack the nitrogen, the better leaving group water molecule will get relieved to produce this kind of 7-membered nitrogen immunocyclic compound. Again the cleaved water which will again attack this positive charge due to water's nucleophilic nature to produce OH here. So, this OH which is enolic form, the nitrogen having double bond as well as the next carbon having OH group, which is generally known as enol, which is less stable, which will undergo isomerization or tautomerization to produce ketone, which is nothing but amide. The entire picture shown here, this is in chemistry name reaction, especially Beckmann rearrangement. This is step, these two will give the caprolactam in presence of acid, the hydroxylamine or oxime, which will give caprolactam, the rearrangement known as Beckmann rearrangement. So, this is bio non-degradable phenol, which can be converted to on the way to get a caprolactam via series of reaction steps, which is undergo ring opening polymerization to produce polyamide that can be biodegradable in nature. So, from non-biodegradable phenol to biodegradable we can convert using chemical synthesis, will produce a caprolactam. Nylon 6, caprolactam undergo polymerization to produce nylon 6. This is a caprolactam. If you heat it 250 degrees Celsius in presence of water to produce, this is a carboxylic acid and CH2 1 2 3 4 5 CH2 is there. So, that is a caprolactam and amine is there. So, again if the reverse you can do the process, what will happen? This carboxylic acid having the hydroxy group and a nitrogen having the amino group, both will combine together elimination of water to produce this caprolactam. If in presence of water, which will produce acid and amine, in removal of water it will give a lactone. The amine can produce lactone, whereas in case of this carboxylic acid, aminocaproic acid AB monomer polycondensation to produce this kind of nylon 6. 2 units of this monomer to link together will produce nylon 6. That means there are 6 carbon will be there. You can count here 1 2 3 4 5 6. So, this is the name of 6, the nylon 6, which is having 6 carbon. Elimination of water to produce this kind of polymer. 8 to 10% of monomer need to extract with water. This is anionic polymerization, where this is our caprolactam, which presence of NaH sodium hydride. What will happen? This sodium hydride will remove the NH proton, which will generate negative charge. This negative charge generated in nitrogen, which will attack the other monomeric unit of the carbonyl carbon, which undergo ring opening like this. This negative charge will attack the carbonyl carbon. This bond get cleave, which is undergo on nitrogen to produce this kind of molecule, then which is again the NH minus, which attacks another monomer unit to produce this kind of dimer. So, like this, the one NH minus can attack the other monomer, which will produce polymer. This is anionic initiated polymer. The initiated anion can attack the monomer unit, the carbonyl group, which will again undergo ring opening of the polymer to produce this kind of dimer. Again the another dimer which can be attacked with amino group, which is having negative charge, to get trimer. Like this, keep on expanding to get this kind of extended polymers. Anionic ring opening polymerization shown here. So, summary, in the whole class we have seen what is the polylactic acids and how is the industrial synthesis, how the chemical synthesis, what is the importance of polylactic acid, especially which is biodegradable nature. The degrading period is around 45 days to 60 days, and what is the industrial application, all these things we have seen. And another class of polymer is polycaprolactone, that also we have seen in details, synthesis and anionic, cationic, followed by coordination polymerization, etc. So, these are all the questions. What is the polylactic acid, uses and application of PLA, means polylactic acids, how to make a polylactic acids, what is the polyamides, that means nylon 6, give the applications of polyamides. Within this, today we end our session. Thank you.